In this video, we're going to talk about Stirling's approximation. Stirling's approximation is a way of approximating the factorial of a number, or in this case, the natural log of the factorial of a number. The reason that Stirling's approximation is nice is factorials show up all the time in statistical mechanics, and they're pretty hard to work with. And so what we would like to have is a simple form that we can replace factorials with. So Stirling's approximation in the end says that the natural log of n factorial looks like n times the natural log of n minus n. And the simplest way that I know of to reach this conclusion is to start with the natural log of n factorial and explicitly write it out as the natural log of the product of all of the individual terms in n factorial, and then use the property that the natural log of a product of terms is equal to the sum of the natural logs of each of the terms individually. So we have the natural log of n plus the natural log of n minus 1, etc. And finally, we can write this down as a sum. So far, everything that I've written is completely exact, but now we take a leap and we say if n is big enough, then this sum really looks like an integral, right? What we're saying is that the steps between each of the n's, right, that the difference between n and n minus 1 is infinitesimally small. We are turning our sum into an integral, and now we can just take this integral. This integral can be done through integration by parts. You can look it up at a table. The result of the integral is this here, where we plug in values of 1 and n. When we plug in the limits, we get this expression where the natural log of 1 is 0 because e to the 0 is 1. And then we throw away the 1 because in comparison with n, assuming n is a large number, 1 is a very small number, right? So we just throw that away and we end up with Stirling's approximation. We can get an equation for n factorial without the natural log by taking e and raising it to both sides to undo the natural log. And what we find is that n factorial looks like e raised to the n natural log of n minus n. And we can further, let's call this e raised to the natural log of n raised to the n multiplied by e to the negative n. And then this turns into n. So finally, we can look at the full Stirling approximation here, where we've added an extra square root of 2 pi n here. In general, the square root of 2 pi times n is going to be very small in comparison with n raised to the n for any reasonable n number. So we are, in general, going to not worry about this 2 pi n square root here. In general, we will mostly be using the version of Stirling's approximation dealing with the natural log of n factorial.
Here we have some values for the natural log of n factorial, along with values for Stirling's approximation of the natural log of n factorial, where we have included the square root of 2 pi n in the bottom line, and we have not in the second to bottom line. And what you can see is that clearly this is a very poor approximation for n equals 1, but by the time we get to n equals 100, we are within 1% of being correct, even if we leave out the root pi square root of 2 pi n. And if we reach 10,000, we are very, very close. And given that most of our systems are going to have on the order of 10 to the 23 or more particles, our n's are going to be very, very large, and the difference between the natural log of n factorial and the natural log of n factorial minus n, or n times the natural log of n factorial minus n, as in the second line, is going to be very, very small. These are going to be essentially the same thing for any reasonable numbers that we are going to use.